Okay, I'm going to do something a little bit different this time. I'm going to visually try to demonstrate how I came up with the solution for the issue that I was talking about in the last video. So first, to recap, the issue was the main issue is that every chunk has many values inside of that area, inside of its boundaries that we need to calculate. So let's say this is a chunk. Let's say it is 32 by 32 in size. Well, then that means we have to use the noise algorithm to calculate a value for 32 times 32 points in the chunk, because this one is 2D. But since we're dealing with 3D chunks, then it's actually 32 cubed, and that is a lot. That is actually almost 36,000. Plus, we have an extra one on each side, because if you have, let's say you have this, like, let's say it's a 2 by 2 chunk. Well, then you actually have 3 values, because you have one here, one in the middle, and then an extra one on the outer edge. So that's the case whether it's 2 by 2, whether it's 4 by 4, or in my case 32 by 32. You actually end up with 33 by 33, and then for the 3D chunk it is 33 cubed. And 33 cubed is, so it's about 36,000 values in total per chunk. So that's quite a lot. But we have, as I mentioned in the previous video, we have many chunks that are empty. So if a chunk has terrain through it, let's say like this, then we can assume the values at the bottom are negative because they're underground, and the values at the top are positive. Or actually, in my case, it's reversed. Sorry. Positive means solid in my case. So if you have a positive value, then that represents solidness, and negative represents empty space. And so if it looks like this, if your terrain is below, then every corner will be the same sign. So in this case, they'll all be negative because they're all in empty space. And that is the simplest solution. But the problem is the terrain can look like this. So what do you do in this case? All corners are negative, but you still have terrain coming through. And so in this case, if you skip generation on this chunk, then you'll have an open, you'll have the mountain here will have an opening at the top. It'll be missing. So that's not good. So this is obviously quite a tricky problem, because it's a balance essentially between optimization, generating fewer values, doing fewer calculations, and also accuracy, making sure that you don't skip any chunks that are needed in order to have accurate terrain. So for programming challenges like this, it always makes sense to start from the simplest point possible. So in this case, my first approach was actually to just remove the 3-dimensional element to it, and even the 2-dimensional element, and just work with 1 dimension. So let's imagine we just have a line, and this way it's just super simple, right? You have your ends of the line, and let's just say this line is, again, this is, let's say it's 32 points long. So here is point 0, and here is point 32. Now let's say both of these endpoints are, well, let's say first, if one of them is positive and the other is negative, then that part is done. We already know that that there's a crossing of the threshold, so we can move on from this part of the function. But if they're both the same sign, then we have to continue. And so what we do in this case is we actually check the point in the middle, the halfway point. Oops. Yeah, let's make it look a little nicer. Halfway point. I don't use this software very often, so I don't really know. There we go. So we check here as well. And if, let's say, the endpoints are negative, and this point is also negative, then we actually want to look at the values in this case. So let's say this one is negative. And also let's say the terrain, just for the sake of this example, let's say the terrain just barely pokes through. It comes through like right here, or yeah. Oh, that looks pretty good. Let's say the terrain just pokes through right there. So so the quickest way to find it is to check the. Oh, and also it's important to mention that the reason this approach usually works is because the terrain is generated using a noise function, and so points that are next to each other are typically going to have similar values. There's a consistency to it, which is why you don't get a lot of erratic looking terrain usually, unless you really tweak the noise function to be very high amplitude. But in our case, it is relatively mild, at least for now. So we can assume that points that are next to each other are going to be similar in value. So in this case, let's say we have, let's say this one over here, because this is far from our actual terrain. So this one would probably be, I don't know, negative 10. So we can call that negative 10. I can even put that here, negative 10. And let's say this one is negative 4. And this one is negative 3. So now we can see that obviously we are closer to the terrain on this side than on this side, because this side just has such a low value. So the next thing we do is we just repeat the process and cut it in half again. And now let's say this one is negative 3.5. Or actually, wait. No, because this is closer to the terrain. So let's call it negative 2. Yeah, so now we're getting closer. So then cut it in half again. And now let's say this one is, it probably would be like, let's say, I don't know, negative 2.1, something like that. So we cut it in half again. And we finally get a positive value. And that's really it. I mean, that's how it works, Kind of seems simple when it's in one dimension. But now let's add a dimension here. So remove. Let's add a dimension. So now let's go back to, oh geez, hold on. All right, let's go back to a square. And now, as you can probably already figure out, the process here is, well, it starts with just checking the corners. And let's say, we have all negative values again. So we check the middle. And let's say the middle is also negative value, but it's much closer to 0. And the second closest, let's say, was this corner here. So then we get the middle point again. So let's go to the middle here, like about there. Then we check this. And we're checking these points as well. So every time I check an inner square, we're checking all 4 corners each time. And so every time we run the function, we're just checking 4 corners of a square. And then based on that, whichever of the 4 corners is the lowest is the direction we move in. So let's say this one, or not the lowest, but the closest to the threshold, in this case, 0. So let's say this one is closest to 0, but they're all still negative. Then we check here. And that's our next inner circle. And we just repeat the process. Let's say this one is smallest, so then we make another one. And I mean, theoretically, you could keep doing this. Say this one. You could keep doing this pretty much infinitely, right? Because there's always another half. But in this case, because we have a constant distance between each scalar point in the scalar field, there is actually a limit. And thankfully, because the size of each chunk is only 32, which, I mean, before 32 seemed massive, right? Because when you end up with 32, or in our case 33 cubed, that is about 36,000 points. But when you're doing something like this, 32, I mean, you can cut 32 in half. You get 16, so that's 1 halving. Then 8, that's 2 halvings. Then 4, 2, and then 1. And once you get down to 1, you can't cut it in half anymore because the distance between each scalar is 1. So you can only have it 5 times. And that makes this very, very fast. This is a very fast check. And if you get to, 5 halvings and you don't find any threshold, all of the corners of every, inner cube or inner square is all the same sign, and it never crosses the threshold, then you can be relatively confident that that no terrain is poking through. Now, there are edge cases to this that I've already discovered, and I'll show that when I actually show the project again. But let's say your terrain pokes through here, and like it can be a skinny mountain peak that pokes through right here. Well, this is not necessarily going to be found because it depends on this corner here having a value that's closest to the threshold. And in this case, or in many cases, that's not what ends up happening. You can have this one and then this one and so on. Oh, I just realized I did this wrong. This doesn't make sense because this inner circle is outside of this one. But anyways, you get the idea. I butchered the demonstration there, but anyways. So in this case, this would be the corner when you do the first check on the entire chunk. This corner would be the one with the closest value to the threshold, but the terrain is actually here. And so we're actually missing it in this case. And this can happen, because the noise function it's not guaranteed to give you consistent, very consistent values. You can have some surprises, essentially. And that's how you get the edge cases. So that is how this technique works. And now I will I'll show how it looks in the project and the performance improvement. All right, so we're back in the project, and I have the same seed and everything. So this is the same terrain that we had before. And I remember this chunk was missing before, so this one is there. Oh, and also you might notice I now have some extra information here on the screen. This is just the average amount of time it takes to generate each chunk. And when I did it without this optimization, it was still pretty low. I mean, it was like 10 milliseconds per chunk. But 10 milliseconds. and sometimes higher, depending on what I'm doing. Like right now, I'm recording my screen, and I'm using a microphone. So these things all are using processing power that can slow down the parallel chunk generation. So might not be totally accurate, but so far, yeah, this is matching more or less what I expected from the testing that I did before. So before it would be roughly around 10 milliseconds, sometimes a little less, sometimes a little more. And this is average. So this is including chunks that have terrain and including those that do not. So getting from 10 down to around 2.5, sometimes 3, is a huge improvement. I mean, it's very good. But well, let's continue here. So I remember there was more terrain back here. I think it was around here that was missing before, but you can see now the stepping through the chunk to try and find where the terrain is working. And if I keep generating more, you can see they're generating very fast and no holes in the terrain yet. Oh, there's one. Yep. And I expected this. So let me actually go. There was one that I was investigating a little bit more closely. I wrote down the coordinates here. It's 450. Oh, whoops, I went the wrong way. Oh my gosh, I'm getting lost. Hold on. Okay. It's this way. Yes. Okay, it should be around here somewhere. All right, 450 to... Ah, there it is. Yeah. Okay, so this one. This one surprised me a lot because it's a pretty big hole. And I was looking into it. I actually spent a lot of time looking into this one. And I figured out what's going on. It's actually the same thing that I just showed in the example, where basically the chunk is I think the chunk size is good for rendering performance and everything. So I am planning to keep it at 32 by 32. But the problem with having a large chunk size is that doing this step through method. So it starts, this chunk is actually below 0. So if you can see, you can see my Y value here is about 0. You can see the terrain. The terrain typically generates around this level. But this chunk starts below. It starts at negative 32. And somewhere like around here, I think, at negative 32. So when we step through, it goes to a halfway point at negative 16, and the other halfway points. And if you just look at it from above, so I'll try to kind of estimate where it was. So the first lowest point of the chunk was about here, and then the halfway point was about here. And once you get here, it actually sees the closest scalar value to 0, to the threshold, is actually over here, like way over here, because these chunks are pretty big. So it actually goes from the midpoint here to here, and then all of the rest of the checking it's doing is over here, and so it actually misses this little hole. Now I do have a potential solution for this. Let me just close this. I've been having some trouble with recording here, so hopefully I don't run into this problem. So I have a threshold here, or a padding value that I can adjust. And now let me run it again. Hopefully I don't have issues here with recording. I know it looks frozen right now, but just I'm loading it again. and then hopefully it'll show up again. One sec. Oh geez, it's not working. All right, hold on. Oh, there it is. Okay, great. So we're back in here, and now let's go back to that location. Trying to increase the camera speed. Yeah, there we go. Okay, right here. And so now you can see that it's not missing anymore. And actually, this is a good way to see it. If you just just go up far enough, yeah, you can see that's exactly where it was right there. And yeah, so the way I solved it is just using a threshold value. So rather than checking each corner to make sure that it's above all corners are above 0 or all corners are below 0. Instead, I give it a little bit of padding. So all corners are above 1.4 or all corners are below negative 1.4. And the reason this works is because basically any chunk that is near the surface, even chunks that are in midair just above the surface, are still probably going to fall within that range. And maybe that's the reason why this chunk average is a bit higher now. It's at 5. Let's see if it stays at 5. If I increase the speed, let's go in one direction for a while. Yeah, see, this is a little bit unfortunate. It's definitely slower now with this threshold value, but I guess that's just kind of the trade-off. Oh, and also I am recording, and like I mentioned before, I think the recording slows it down too. So I'll have to check it again when I'm not recording. But this is still, it's still takes about half as long as without the optimization. So it's still very good. And I mean, I can't imagine I'm going to need it to be any better than this. I mean, faster is always better, but at this point, I'm not sure how much faster it could get. So yeah, I mean, that is it really. I haven't done much exploring around to look for more holes in the terrain. I'm sure if I explored enough, I would find some. I do not doubt it. It's very possible. It's it's unfortunate with the nature of a noise algorithm. There's not really any way to predict it accurately or reliably. It's going to be random. That's just how it works. So the edge cases are going to come up. I'm sure, especially once I start really tweaking the values for the terrain generation, getting more variety in how the terrain looks and everything. I think at that point it's going to be even less predictable, and so yeah, there might just end up being inconsistencies and holes in the terrain, which is it's unfortunate, but that's just the nature of it. That's I don't know if there's much getting around that. Maybe you could set some, have a setting that adjusts the threshold that I was talking about to make it much higher for, users who have faster computers or more cores, This is my laptop has 8 cores, by the way. It's not, I know I said in an earlier video I said quad core, but that was a mistake. It's 8 cores. So maybe that's a reason why this works pretty well and goes pretty fast. I think if I was on a quad core, this would be much slower, much slower. But yeah, so if somebody has 16 core or something like that, then maybe for them they could easily increase the threshold to get more accurate terrain, fewer issues. So that's always an option. Having something like that in place would be good. But yeah, I mean, I'm not seeing any more issues, to be honest. This seems seems like I found a pretty good threshold to use that is pretty reliable, at least for now, with this type of terrain. Yeah. So I guess that's it for this issue, for this programming challenge. It was definitely a tricky one, and I know the resolution, it's satisfying, but it's also a bit unsatisfying given how unreliable it is. But that's just how it is this time. Yeah.